All right, and we're back. Factorial of 4 is 24. Factorial of 5 should be 120, so on and so forth. Make sense? All right, so now we know how to do repetition. We've learned the entire language. We can define variables, we can ask questions, and we can do repetition. What's up? We're going to. Oh. Okay, so now let's look back at the book here, and we're going to start coding a few things that the book wants us to talk about, but I'm going to very specifically not code certain things because that's going to be your impossible homework assignment. So I'll have you look through some of these things. I'll just kind of cover at a real high level because some of these things you should have either already known or I'll just let the book teach you. So ASCII Unicode, what are those two things? So this is how characters are, character sets, this is how characters are represented in programming languages. So ASCII is a 7-bit number, 127 unique characters. Technically, the original definition was 256 with 8 bits, but it's the American Standard Code for Information Interchange. Basically, an A is a certain number, a B is a certain number, a C is a certain number. Why is that? Because computers like numbers. Humans like letters, computers like numbers. Question mark would be a certain number. Down here, here's the set. So like a capital A is the number 65. Capital B is a 66. Capital C is a 67, so on and so forth. Lowercase a is a 97. Dollar sign is a 36. These are 7-bit numbers. Make sense? All right, so this allowed us to encode characters as numbers in computers. A lot of times we don't want just a wall of zeros and ones or a wall of numbers. We want strings like hello world and things like that. Well, in order to store hello world, we have to store the H and the E and the L and the L and the O, so on and so forth. Okay, but we need to encode the H with its, at the very least, ASCII equivalent. So we actually store, if it's a capital H, the binary version of 72. Which is 1001000. Right? And just as a real quick refresher, binary to decimal. So if I have, what did we say an H was? An H was a 72. So if I have the number 72, let's go decimal to binary first. That way I can go the other direction. I'm going to show you both patterns, and this pattern exists for conversion between any number systems. So decimal to binary, if I have a 72 and I want to convert that into its binary equivalent, what I'll do is binary is base 2. I'll repeatedly divide this guy by 2. Now, some of you might kind of hard code it and say, okay, well, I have the ones place of 2s, 4s, 8s, 16s, 32s, 64s, but any bigger than 64 and beyond is 72. So I'll put a 1 there in the 64s place. Now, how much more do I need to get to a 72? And you might kind of figure out where your 1s go, but this will work every single time in terms of a pattern. So 72 divided by 2. 72 divided by 2 is 36. So that's going to give me a 36 with a remainder of 0. 36 divided by 2 is an 18. 18 times 2 is 36 with a remainder of 0. 18 divided by 2? 9. 9 times 2 is 18 with a remainder of 0. 9 divided by 2? 4. 9 divided by 2 is 4. 4 times 2 is 8 with a remainder of 1 to get to 9. 4 divided by 2? 2. 2 times 2 is 4. Remainder 0. 2 divided by 2? is 1. 1 times 2 is 2. Remainder 0. 1 divided by 2. How many times does 2 go in the number 1? 0 times. 0 times 2 is 0 with a remainder of 1. We know we are done when we get a 0 there. We read our answer from bottom up. 1, 0, 0, 1, 0, 0, 0. And that should match up to our 72 here. 1, 0, 0, 1, 0, 0, 0. Make sense? Okay. Now if I go the other direction, binary to decimal, we start off with that number. I'm going to put some spaces in here. 1, 0, 0, 1, 0, 0, 0. All right, so we know that's the answer, right? Okay, so this is the 1s, 2s, 4s, 8s, 16s, 32s, 64s. This is the 64s place, 32s place, 16s place, 8s place, 4s place, 2s place, 1s place. The far right is always in the 1s place. All right, if we want to write this a different way, this is 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5, 2 to the 6. So this is 2 to the 6th place, 2 to the 5th place, or 2 to the 5th power, rather. 2 to the 4th power, 2 to the 3rd power, 2 to the 2nd power, 2 to the 1st power, 2 to the 0th power. Anything to the 0th power is always 1. Far right place is always the 1's place. Times 2 is the 2's place. Times 2 is the 4's place. Times 2 is the 8's place. Times 2 is the 16's place. Get it? All right. So then what we do is we go through and we say 1 times 64 plus 0 times 32 plus 0 times 16 plus 1 times 8 plus 0 times 4 plus 0 times 2 plus 0 times 1. Whatever. And this is going to give us 72. So that's 64 plus 8, which is 72, plus nothing else. See the pattern both directions? All right, and just to show you, you didn't actually just learn anything new. Because what if I wanted to convert decimal to decimal? This is the number 72, and I want to convert that to decimal. Divide that by 10. 72 divided by 10 is 7. 7 times 10 is 70. Remainder 2. 7 divided by 10. 10 goes in the 7. 0 times. 0 times 10 is 0. Remainder 7. We have a 0 there. We know we're done. We read our answer from bottom up. 72. The other direction, decimal to decimal. If I have a 7 followed by a 2, this is 10 to the 1's place. Well, here, this is the 10's place. This is the 1's place. This is 10 to the 1's place. This is 10 to the 0's place. So this is 10 times 7 plus 1 times 2, which is equal to 72. Make sense? All right, so that pattern works no matter what our bases are. Things get a little bit weirder when we deal with hexadecimal numbers. So popular bases are 2, 8, 10, 16. This is binary. This is octal. This is hexadecimal. This one is decimal. Why is decimal popular? 10 fingers, 10 toes. Easy for us, right? All right. Why is binary popular? Computers, digital logic, right? On, off, 0, 1. We need 2 states. All right. Why is octal popular?
Shorter, 3 times shorter than.
Okay, then why is hexadecimal popular? Hexadecimal has been used to represent colors, but the flip side is why has it been used to represent colors?
Because it's a lot. Because it's a lot.
We have a lot of colors, right? Isn't that like the thing that keeps like 24-bit color or something like that? 24-bit color means we have 24 zeros and ones. And 24-bit color in a unsigned number, since you don't need negative colors, is 2 to the 24th power. That's how many colors there are. 16,777,216.
If we're doing colors in hexadecimal.
Huh?
If we're doing colors in hexadecimal.
Well, no, that's the number of unique 24-bit colors there are. Yeah. So it's actually 16,777,217 because it's 0 to that number. That's the number of unique colors we can represent in 24 bits. So we can write it this way in decimal, which is less than 24 total characters. Or we can write it in 24 bits, a bunch of ones and zeros up to 24 of them. Or we can even compress it more by writing it in hexadecimal. Okay? But now there's a trick. So then we could say, well, why not go more than hexadecimal? Why not do base 17 or 18, 19? You don't have 16 fingers. Or is this a reveal? Tell us about your planet. It's got to be something special about octal and hex. What about base 3, 4, 5, and 6, and 7? Base 9. Why did we stop at 8?
Because 8 is 2 power of 3.
Okay. Seems like it makes sense. All right. Why do we stop at 16?
16 is double for 8.
Okay, so what would be the next one that would make sense?
32.
32. All right.
Why aren't we ever use 4?
That's a good question. We could use 4 by the same reason. We actually do use 4. We typically don't think about things in terms of base 4, but I'm not even sure the book talks about this. Let's just assume it does. We talk about bit stuff. 1 bit is 0 or 1. 1 byte is 8 bits. What do we call 4 bits?
Half byte.
Yeah. 4 bits is called a nibble.
Isn't there like a name for like 2 bits?
There might be. It's not real commonly used. Since it's not commonly used, and Actually, I don't even think there is. I don't think there's
I
a.
thought in class, like last class that you talked about this, there was another name for something.
You're maybe thinking about words and double words.
Oh, okay.
Those are much bigger,
Yeah.
bigger values. All right. So this is. So we do have this thing called a nibble sometimes, where we think about something in terms of 4 bits. It doesn't matter. Who cares? Usually we think about things in terms of bytes.
Do you still make your 2 number programs class whatever you have a paper on there?
I don't know. Write a paper on.
Differences between binary, octal, and decimal?
Maybe. Depends on my mood. Or whether I decide to tell them in class or accidentally tell them in class. So here, let me go and show you the hex thing real quick. So we'll use my favorite hexadecimal number, 2989. So we'll say decimal to hex. All right, so whenever we go from decimal to another base, we use that pattern of dividing by the base. So 2989 divided by 16, my base is 16, 2989 divided by 16 is 186. 186 times 16 gives you 2976. So that's remainder 13. 186 divided by 16 gives me 11. 11 times 16 is 176, so that's a remainder 10. 11 divided by 16 is 0. 0 times 16 is 0 with remainder of 11. We have a 0 here, so we know we're done. We record our result, 11, 10, 13. Now, in binary, base 2, our legal bits are 0 and 1. In octal, base 8, our legal octets are 0 to 7. Decimal, base 10, our legal digits are 0 to 9. Hexadecimal, base 16, our legal hextets are 0 to 9 and A through F. So an A is a 10. So this guy is actually an A. A B is an 11. And a 13 is a D. So this is BAD, bad. All right, and it works the other direction. BAD, hex to decimal. So we have B, we have A, we have D. We need to map those to their actual values. This is an 11. This is a 10. This is a 13. This is a 16. Actually, let's see, it's 1. $40.96, 16, 1.
Well, I think you accidentally did 16 to the 3rd power for B.
I did. 256, thank you. So this is 16 to the 2, 2nd power, 16 to the 1st power, 16 to the 0th power. So that means this is 256 times 11 plus 16 times 10 plus 1 times 13. Add all that up. 2989. Okay, so we understand how those work. Now, those two patterns we just wrote, we can use for converting between any base and decimal, as well as decimal to any base. Doesn't matter what the bases are. All right, now we're back to the more important question when it comes to a computer architecture class. Why specifically? We already know the 10, right? This is the whole people suck thing. All right? 10 fingers, 10 toes, computers are cool, people suck, that's just the way it is. So this 2, 8, 16 thing, this is more of the computer world thing. Computer architecture, we think that's cool in here, that's what we're gonna focus on. So we already answered the question, why base 2? Digital logic, zeros and ones, we only need 2 representations. Binary is the answer, right? We start looking at quantum computers, and you're actually gonna start needing base 3. Because quantum computers actually have 3 states. They have on, off, or both. It's called spin. So before long, when we all have quantum computers sitting on our desks, this class will probably have to have a old school computer architecture class when we're still talking about binary, and then we'll have they're called qubits. Quantum bits are called qubits, where it's either on, off, or spin, where it's both. All right, so binary makes sense. This is digital. What about octal and hex? Now you did point out that these are powers of 2, right? We kind of point out like, base 4 could work. What if I asked you this question? BAD hex to binary. Using only what we've discussed in class so far, what would you have to do? You'd have to convert BAD first from hexadecimal to decimal, giving us 2989. Then you would convert, so that would give us 2989. Then you convert 2989 to binary by dividing it by 2 over and over and over and over again, recording the remainders, reading it from bottom up, giving us a whole bunch of zeros and ones, right? Or BAD this is an 11, this is a 10, this is a 13. What's the largest value in hexadecimal? Binary is 0 to 1, octal is 0 to 7, decimal is 0 to 9, hexadecimal is 0 to what? 15. 0 to 15. 0 to the base minus 1, right? Base is 16. So 15 is the largest value we need to be able to represent in hexadecimal. How many bits does it take to represent 15?
3.
111. What?
Represent 15. 1.
How many bits? What's a bit? A single 0 or 1. So I need to represent the decimal number 15. Let's just start with that. I need the decimal number 15 in binary. So Blade said 111. This actually gives you a 7. 1111 gives you a 15. Now, can you represent a 0 in 4 bits?
That is 0, 0, 0.
So with 4 bits, I can represent every single one of the hexadecimal values. Right? So an 11 in binary is what?
1011.
It's that. A 10 in binary is what?
1010.
A 13 in binary is what?
1101.
Take the spaces out. There's BAD in binary. Make sense? It's because it's a power of 2 that we're able to deal with it in groupings of 4. And we already saw a little forward-thinking punchline with octal. Octal, the legal values are 0 to 7. Smallest value, well, how many bits does it take to represent a 7? 3. 111 is a 7. Can you represent 0 in 3 bits? 0, 0, 0. So any octal number, so if I just pick a random octal number, how about 129? Is that a legal octal number?
Yes.
Okay. Tell me why she's wrong.
Oh, no, because the 9 isn't legal.
9's not legal. So biggest number we're going to have is a 7. So if I do 127 octal to binary, we have 1, we have 2, we have 7. We do it in groupings of 3. So this is 0, 0, 1, 0, 1, 0, 1, 1, 1. So this is 0, 0, 1, 0, 1, 0, 1, 1, 1. That's 127 in octal represented in binary. Technically, these first 2 zeros aren't needed, so it'll be 0 times that power, 0 times that power. All right, so you see the convenience of octal and hexadecimal. And at some point in the future, if we really need to represent large numbers, because something else that we said was hexadecimal's power is that it allows us to count to really big numbers. Right? That's its power. Without like losing track. Like you would want, if you had to count to 1 billion in binary, that would start sucking quick, right? Counting to 1 billion in decimal, we're not going to do either, but at least it's like somewhat conceivable. Counting to 1 billion in hexadecimal is going to go way quicker. Make sense? At least shorter. You know, 1 billion in a binary is going to be a lot of bits. A lot of bits to get to 1 billion. All right. So, what kinds of things in our computers do we use hexadecimal for? Memory. Yeah. So if we have a computer program, let's see, I have some Java here, right? And I do something like int array AR is equal to new int array, I don't know, 100 or something like that. And then I say system.out, blah, blah, blah. Stop yelling at me. System.out.println AR. This will give me a memory address. It's going to look all hexy. So here, there's a memory address that's hexadecimal, 7852E922. Right? It's technically not on our real memory address. It's the memory address in the Java virtual machine, but don't worry about that. That's a memory address. How does memory work in our computers? What's an address? Let's answer that first. What's an address? What is that guy? Okay. It's the location. Addresses are used to specify a location. So we have addresses in real life, don't we? You know, so typically we have a house number, a street name, city, zip. We have 4 pieces of information to get you the location of an individual house or an individual property. How do addresses work in computers? Do we have a street name? Do we have a city? Do we have a state? We have a number. Computer, every house is on the same street. Big long street, right? So really long street, and you might be housed some gigantic number in hex, right? If you had to reference that in binary, that would be a really scary number. In decimal, it's a pretty scary number. In hexadecimal, it's a less scary number. Hexadecimal allows us to represent large values in small footprints. And luckily, we can represent it in groupings of 4 bits. Represent it in nibbles. Really make sure you enunciate that one, that one well.
Sounds like creep.
Sounds like other things too.
I'm not saying you are creep.
So, addresses in computers. So this is a location. Humans locate things using street number, street name, city, state. Computers locate things using number. Everything's in one long line. Contiguous houses. Every house is right next to each other. Contiguous houses. All right. So, as memory gets bigger and bigger and bigger and bigger, you know, it used to be that, one of my first computers had like 32 kilobytes of memory in it. I remember I had to one of my coolest computer that we had to like wait for the processor to be released was a 486 DX2 66 megahertz computer that shipped with 8 megabytes of RAM. Solid stuff. Yeah, now you buy a new computer. If it's a budget pleaser, it's got 4 gigs of RAM in it, right? Actually, anymore, budget pleasers might have 8.
Yeah.
8 gigs. 16 gigs of RAM is pretty common. 32 gigs of RAM now is usually considered pretty good, right? Heck, my new cell phone has 12 gigs of RAM. It's a phone. I bet you this phone has more RAM in it than at least some of your laptops. Who doesn't have at least 12 gigs of RAM in their machine?
I think I have 8.
Huh?
I think I have 8. It's a MacBook Air.
Yeah.
I think
Phone. It's a phone.
Is that a Note?
It's Note 10.
Didn't you get that like a year ago?
No, I got the Note 9 a year ago. I use that as a soap dish now. This is a
How
Note,
long ago did you get that one?
I don't know, 4 days ago?
Really?
Yeah, it just came out. I got it at release day.
I think it's like 2 weeks ago, right?
I don't think so.
Last time we made, you said you got it.
I think it was last week. I think I got last Wednesday. That's when it shipped.
That's not 4 days.
Oh, whatever. A lot closer than a year ago.
So you're one of those people that gets a new phone every year?
What do you mean, those people?
Still have my same old phone.
What do you expect?
Good point.
Well, and I'm a computer scientist. I kind of write software for him. I should probably know about the newest stuff. I mean, wouldn't it suck if I was talking about computer architecture up here when my most recent architecture was that 32K machine from, unless I'm faking it. Maybe I just don't know about this stuff. I'm like 15 minutes ahead of you. Mr. Gonzalez has got an earpiece. He's feeding me the lines. Yeah, so memory is big, long street inside of our computers. Now, before I start rattling off those words too much, I just want to make sure we put this chart in there. Most of you should know, actually all of you should know this, but just in case. Number convert, let's go size conversions. Conversions. So if you didn't know this stuff that I'm about to show you, don't tell me, but learn it. So the guy over here on the left is going to be our bits. The guy over here on our right is going to be our bytes. So we have 1 bit. We have 1 kilobit, lowercase b, is 1,024 bits. 1 megabit, lower b, is 1,024 kilobits. 1 gigabit, little b, is 1,024 megabits. And then we'll just put terabit on there, even though nobody says that yet, but eventually they will. Okay, 1 terabit is 1,024 gigabits. Okay, gigabits, that word's used now, but we'll talk about that here in a second. We have 1 byte is 8 bits. 1 kilobyte, big B, is 1,024 bytes. 1 megabyte, big B, is 1,024 kilobytes. 1 gigabyte, big B, is 1,024 megabytes. 1 terabyte, big B, is 1,024 gigabytes. That makes sense? And then the example I always use, where consumers probably should get screwed over, but technologists shouldn't. I'm going to go ahead and test this. Again, I ask this every single time, and several of you in this room have been on the receiving end of me yelling about this, and I know I'm about to get angry because you're probably still not going to know the answer. How fast is your internet at home? Too slow, it doesn't count. I want the speed of your internet. 200 megabits. Megabits, little b. Okay, not 200 megabytes. Now, one thing you'll see in the commercials, what do? They call it meg. 200 meg internet. That way they can lie without lying.
Megabits are not bytes. There's a huge difference.
Okay. So when you download something with a 200 megabit per second, little b, in order to get that into megabytes per second, we have to divide it by 8. So that is 25, max 25 megabytes per second download speed. It's maximum theoretical download speed, because you're still limited by whoever the person sending it to you is. Okay? If that guy's up on a dial-up modem, I don't care if you have a gigabit internet. You're not going to get it any faster than 3.36 kilobytes per second. All right? So understand how those numbers work. Okay? Internet connectivity is where it's the funniest thing, because as technologists, every one of us in this room should know exactly how fast our internet is. And it doesn't have to be a high number, because maybe you've decided, oh, I don't need the fastest that they offer, because what I use my internet for is sufficient with X. But you as technology experts should know that, right? You should be able to tell me what the theoretical maximum download speed of your connection is. So we had a too slow. And what's even worse about that is she's recently purchased it. Right?
They say it's 200, but I don't know what it actually is.
Okay, so it was sold to you as 200.
Technically, they say up to 200.
Oh, okay. So it was sold to you as 200, or is this defense we're playing now?
I think it's sold to me. That's what she said.
Okay. So you have Spectrum?
Yep.
Okay. So you have Spectrum's normal internet, which I think usually is 200 megabits per second. It used to be 100 a year ago, and then they doubled it. All right. Anybody have more than 200? Anybody have less than 200? Anybody with DSL or something? What do you have?
Like 60.
You have 60? Is that, well, that's over cable modem.
What?
So you have 60 megabits, but it's got to be a cable provider, not DSL. Okay, but so you're a smaller community, I'm guessing.
Yeah, on the front step.
Okay, yeah, because I mean, 60 is pretty slow for cable modem providers now, but it's actually like, for instance, the fastest DSL you can get in Grafton is 24 megabits over DSL, which is a telephone line type connection.
Isn't that through AT&T?
Yeah, through AT&T. But AT&T has a fiber connection. They have gigabit fiber in Milwaukee. They're about to bring gigabit fiber to Mequon. I'm waiting for them to bring it to Grafton. I have gigabit spectrum in Grafton, but everything else I have is through AT&T. So I would actually save money by having my internet through AT&T as well, but I'm not going to operate off of 24 megabits. So, but yeah, so 60 is a number that sounds like cable modem to me, but it's a small community. Anybody faster than 200? What do you got? 300? You're over in Michigan, right?
Yeah.
All right, so you're Ann Arbor?
Yeah.
Who's the provider?
80.
Really? I figured they would have one of the big brands. Because right now, basically, Spectrum and who's the other one? Just split up the country. Comcast. Spectrum and Comcast. Spectrum absorbed Time Warner, and then they just went through and they just divvied up the country. So effectively, it's not a monopoly. That is a monopoly. It's a very interesting technology talk at some point. It's if you go into any community that matters, let's say, but I would almost stick by that thing of any community. You will always have at most one cable modem provider. There will never be competitors because the competitors have kind of agreed upon which land they will own. And they just stay out of each other's backyards and just make their money because now they can charge whatever they want. So I'm up in Grafton. If I know anything about internet speed, my only option is Spectrum. I wouldn't be able to stream 4K Netflix over 24 megabit per second. So the fastest AT&T can give me, I watch a lot of Netflix. I couldn't get the best quality Netflix off that.
They offer only 5 megabits per second too.
Who?
AT&T.
Where?
I just put in my address and
In the sticks? Are you in the sticks?
I'm in New Berlin.
Yeah, so you're in the sticks.
It says 5 megabits per second or 50
Oh, well, so
for $10 more.
yeah. So the 5 is like, hey, you need to check email. Or your grandmother needs to check email.
Yeah.
No. You need water?
I need more.
So fast, you said no.
Well, if we take a break,
Like
then
3 minutes.
we'll just go get water. I'll just keep going.
That's not how it works. I don't want to miss it. That's Maddie.
I second her need to take a break.
All right, I will pause for 3 minutes. 9:25. I'm not even I'm going to pause the record. It was like, it doesn't even sound impressive because it was like 98 degrees, which doesn't sound that hot.
But humid.
It wasn't. It was humid, but the ground is made of stone. You are in a pizza oven. I'm telling you, you're walking around and your calves hurt because they're cooking. I've traveled a lot. I've been to some places. I've been to India. Nowhere close to Israel. You got grass in India. You got dirt. It's fine. Right? No big deal. You got those room air conditioners. What made it even worse is in Israel, we're visiting all these churches and things like that. You always have to have your legs covered. So we had to wear pants. I couldn't even wear shorts. So hot. Ridiculous. All right. Am I recording? I'm recording. All right.
Moral of the story?
Which part?
Wear pants.
Well, no, that wouldn't have been my preference. I also got my arm pooped on at the whaling wall.
By what?
I assume a bird, but I mean it is a reasonable question. Yeah. So 2 rabbis and I walk up to the whaling wall, and I leave with poop on my arm. But yeah, so it's like this thing. So I go up, I have like my hand up on the wall, and something, goes. Now, this is like an extremely holy place, right? And I mean, you can't just like wipe your arm on the wall. Somebody's going to shoot you. You can't do that, right? And they're right next to the wailing wall. If you're standing there facing it to the left is this place they call the Holy of Holies, where only the Jews are allowed in there. Okay. Well, I have my nose, so I got the entry card. Okay. So most of you, I think, know I grew up Jewish, but I'm Lutheran now. But in any case, I go over there. They hand you a yarmulke to take in with you. So I'm here thinking, do I wipe the poop off with the yarmulke? The yarmulke is this little hat you put on, because you gotta have your head.
First thing you think.
I mean, this is not like just a little bit. Okay, I mean, it was a direct hit by somebody who had, I don't know, burritos or something. It was something. Yeah, so I went through the whole place, and then came back, and then I made my wife cut baby wipes out and cleaned me up, because the whole rest of our group was like waiting on me, because I was the only one allowed to go in. I mean, that's like bucket list stuff. You can't pass that up. There's people there with like rifles and things like that.
What's the nose thing?
The Jewish nose. Yeah.
What's a Jewish nose?
Oh,
Have big noses.
Yeah, it's just you guys Google it. It's a thing.
I
Yeah.
don't know if I should. Flip the new back.
All right. So we should all know our speed of our internet connection. More importantly, we should understand size conversions is going to be very important for us, because sometimes we're going to be dealing with registers that are 8-bit or 16-bit or 32 or 64-bit registers. We need to know what that means. Okay, what does it mean for something to be a certain number of bits? 8 bits means the value is represented as 8 zeros and ones. All right, now when we talk about zeros and ones, so let's just deal with, we'll do 4 bits right now. So we'll do 4-bit values. So I'm going to say 4-bit unsigned. What is an unsigned value? What does it mean when I say unsigned? Yeah, only positive numbers, right? We're going to give up our ability to store negative values. Okay? So 4-bit unsigned value. 4 bits means what? 4 zeros and ones. 4 bits, 4 zeros and ones. So the smallest 4-bit number is 0. Largest 4-bit number is 15. And then the count in between that's a 1. That's a 2. That's a 3. That's a 4. That's a 5. That's a 6. That's a 7. So on and so forth. Okay? So those are 4-bit unsigned values. So we can hold numbers between 0 and 2 to the 4th power. I'm sorry, 2 to the 3rd power, which is 15. All right. So what if I want signed values? Or 16, sorry. 4-bit signed values. So signed values means that we now have the ability to hold positive and negative numbers. Make sense? All right. So, but what is it going to cost us? So we have the ability to store negative numbers. It costs us 1 bit. Price of admission. If you want to hold negative numbers, you're going to give up one of your bits. All right? So the range of values, range of 4-bit values, unsigned is 0 to 2 to the 4th power minus 1. So in this case, 0 to 15. Signed is negative to a positive number, but the punchline will be it's -8 to +7. That's the range of values you can actually hold. But let's think about how it can do that. So we're giving up one of those bits. So we're going to say it's plus or minus 2 to the 3rd power. Okay, and 2 to the 3rd power is an 8. So we'll roughly say this is -8 to +8. Roughly. So this really comes down to depends on how we represent negative numbers. Okay? We have some options. So one option is we do something called sine and magnitude. So sine and magnitude, and I'm going to do this in 2 columns here. So that means our values are only 3 bits. So we have 0, 1, 2, 3, 4, 5, 6, 7. And I'm going to copy that, put it over here. So we'll say that negative have a 1 at the beginning. And positive have a 0 at the beginning. All right, so this is sine and magnitude. Let's see, where is our... So this is a -0. This is a +0. Is that problematic? No. It's just wasteful. We have 4 bits to work with here. It's wasteful to use, it's wasteful to represent a positive and a -0. We only need to represent 0. 0 is 0, right? All right, so this guy accurately represents positive and negative 4-bit numbers with 2 different ways of representing 0, which we would say is wasteful. All right, so that's one way of doing it. And I'm actually going to steal this slide and then modify. Another way is something called the ones complement. So ones complement says flip all the bits. In fact, I actually want to just show you, I don't want to spend the time on ones complement giving time. So ones complement, we flip the bits. Problem is, we can represent all the numbers, but we have the exact same issues we had a few minutes ago. We represent 0 twice. Okay? We have 0 represented as 0, 0, 0, 0, and we have 0 represented as 1, 1, 1, 1. Okay? So, we have this thing called the twos complement. The twos complement says flip all the bits and add 1 to it. All right, so what we're going to do here is I'm going to represent these a little bit different because this is the answer, okay? So we really want to have, for a 4-bit number, we want to be able to represent the values of -8 to +7. That's what we want to be able to represent. Okay? Instead of having -7 to +7 with 2 representations for 0. That's what we have in the other 2 models. The other 2 models say we can represent all the numbers between -7 and +7. We just happen to have 2 different ways of talking about 0. With 2's complement, we're going to say, I want to have -7 to +7, but instead of having a second way of talking about 0, I want to have a way of representing a -8. That make sense? All right. So what I'm going to do here is I'm going to say, we'll do 0. Well, here, I'm going to go -7, -6, -5, -4, -3, -2, -1. 0, 1, 2, 3, 4, 5, 6, 7. And I'll go ahead and I'm going to throw the -8 on here for right now. That's the range we hope to accomplish. Okay? Now, let's do the easy ones first. All the positive numbers we represent just using the 3 bits, with always having a 0 on the left. It's only negative if we know it's encoded in 2's complement and there's a 1 in the far left bit. So all our positive numbers are just always going to have a 0 in the far left bit, and then we'll use the following 3 bits to represent the values. So this guy will be 0, 0, 0. This guy will be 0. Well, I'm sorry. This is actually 0, 0, 0, 0. This is 0, 0, 0, 1. 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, and 0, 1, 1, 1. All right, so we're cool over on that side. All the positive numbers all start with a 0, and then we have the 3-bit representation of 0 through 7. Cool. All right, so now for the negative encoding, we're going to take the normal value. Forget about the negative value for a second here. All right? We're representing those negative values. So, but I'm going to say, what is the 3-bit representation for a 1? 0, 0, 1. Okay, now I'm actually going to represent this 4 bits here. First thing we do is we flip all the bits. So this becomes 1, 1, 1, 0. Then we add 1 to it. A 2, 0, 0, 1, 0. Flip all the bits. I'll just do it next to it here. 1, 1, 0, 1. We add 1 to that, and we end up with 1, 1, 1, 0. Three is 0, 0, 1, 1. Flip all the bits. 1, 1, 0, 0. Add 1, 1, 1, 0, 1. 4, 0, 1, 0, 0. Flip all the bits. That's 1, 0, 1, 1. Add 1 to that. That is 1, 1, 0, 0. Five, that is 0, 1, 0, 1. Flip all the bits. That's 1, 0, 1, 0. Add 1 to it. That's 1, 0, 1, 1. 6. That is 1, 0, 1, 1, 0. Flip all the bits, that's 1, 0, 0, 1. Add 1 to it, that is 1, 0, 1, 0. Seven, that is 0, 1, 1, 1. Flip all the bits, that's 1, 0, 0, 0. Add 1 to it, that's 1, 0, 0, 1. 8, moment of truth. So 8 is 1, 0, 0, 0. Flip all the bits. We have 0, 1, 1, 1. Add 1 to it. We have 1, 0, 0, 0. 2's complement now gives us the ability to store one extra value. Now, it might seem small, but it's actually huge because 2's complement has one additional superpower. It mathematically works to accomplish subtraction through addition. And what do I mean by that? So 3 minus 2 is the same thing as saying 3 plus negative 2. So inside of a computer, if we have a tool called an adder that knows how to add binary numbers together, we can add negative numbers together by using, so we know 3 minus 2 is a 1, right? Okay, in human speak, okay, decimal. 3 minus 2 is going to give us a 1. But now if we map that and we say, okay, well, we have the number 1, 1. So we'll keep it in 4 bits. We have 1, 1, and we want to subtract from that 0, 0, 1, 0. We can learn how to do subtraction with binary. It's not hard. The way subtraction, it's exact same thing that the way subtraction works in base 10. You know, when you don't have enough, you borrow from the guy next to it, but just instead of borrowing 10, you're borrowing 2. Right? You could do hexadecimal subtraction as well. Instead of borrowing 10, you're borrowing 16. Okay? So you could do the math with this, but you'd have to have another piece of equipment inside your computer in order to do this subtraction. You'd have to have a subtractor. All right? Or what we can do is we can say, well, we're going to take that 0, 0, 1, 0, and then we're going to convert the 0, 0, 1, 0 into its 2's complement form. So that is 0, 0, 1, 0, flip all the bits, that's 1, 1, 0, 1. Add 1 to it, that's 1, 1, 1, 0. And then you're going to add those together, which is 1, 1. Actually, we got to start with the right. So this is going to be a 1. Then we add the 1 plus 1, which is going to give us a 0 with a carry. So we have a carry here. 1 plus 0 is a 0 with a carry. 1 plus 0 plus 1 is 0 with a carry. So there's our final answer, 0, 0, 0, 1. That makes sense? All right, so encoding values in 2's complement allows us to store a value as a negative value. It also allows us to accomplish subtraction through addition. 2 important things. Okay, so let me make sure. Let me see if the book talks about anything else that I think is interesting before I start giving you homework assignments and giving you enough of a starting point. All right, did ASCII, unsigned, signed, binary hex, did that. Number bases, we didn't talk about floating point numbers, but that's fine. You'll read about that, go through the exercises. We won't have time to get to that today. Well, really, it's these other things that are going to be more difficult. So what I'll do is, for your homework, the first part of your homework is to go through all of chapter 1 and do all of the exercises. So like here's unsigned binary numbers. You go through here. It has these interactive things you can do, and then it has like quizzes and stuff like that where you can put in your answer. The next higher 3-digit binary number. So 0001, so on and so forth. So go through all those. I'll be able to see on my side that you completed that, because I can see all the students that have the book. All right, so go through that. That way I know you've exposed yourself to the material, let's say. But now I'm going to give you a programming assignment in Scheme, a little practice. All of chapter 1, because we have 8 weeks to go through all this stuff. We got to power through it. Power through it.
It just needs to be done by next Thursday.
Right. Yep. So, what we're going to do is I'll give you some of the starter code here. We want to write several different Scheme functions. All right. So we want to write so let's just do a 1. Function that converts decimal to binary. Well, I'm going to take the 1 off of there. It looks better. Function that converts binary to decimal. Function that converts, we'll do them all. Well, I'll skip octal. We'll just do hex. Decimal to binary, binary to decimal, decimal to hex. Function that converts hex to decimal. And lastly, function that displays, or let's see, that encodes 4-bit 2's complement values. So the idea here would be if you pass this, so for example, I think the first ones are, well, I'll just give you examples for all these. So if you pass this guy a 2, it would spit out the 4-bit equivalent of the value 2, which is, I'm going to give you a little hint here, the list containing a 0, 0, 1, 0. That's what the output should be for a 2. For a negative 2, would produce the list 1, 1, 1, 0, which is this guy with all the bits flipped plus 1. So this is 1, 1, 0, 1. Add 1 to that, we have 1, 1, 1, 0. So this is negative 2 encoded in 2's complement, which is this guy right here, 1, 1, 1, 0. That make sense? All right. These other ones are going to be pretty similar. So I'll say example here. So if I pass in a 5, it should spit out the list containing 1, 0, 1, something like that. And these only have to positive decimal to binary. They only have to work for, the only negative thing we're going to do is this last one, this 2's complement thing. All right. This one, example, if it would take in, so it converts binary to decimal. So if it took in the list 1, 0, 1, it would convert that guy to a 5. That's what it would spit out. Decimal to hex. 2989 would produce the list B, A, D. And the list B, A, D would produce 2989. That makes sense? All right, and you accomplish this with cars and coulters and kanzas. So if we just think about like this first one, if you pass in a 5, what do we do? So let's define des2 bin is going to be a lambda that takes in a number as a parameter, right? And what are we going to do? We're going to continually divide that number by 2, looking at the remainder. Now, we do have a function in here. So if I say 5, if I say mod 5, 2, is it the percent? Percent 5, 2. Oh, modulo, I think it is. Modulo 5, 2. There we go. So 5 divided by 2, 2 goes into 5 2 times with a remainder of 1. That make sense? So the function is modulo. Here's the number. 5 divided by 2 gives you a remainder of 1. So remember, if I converted 5 into binary, I divide 5 over and over and over again. So let's go and look at this here. That's our example. 5 des2 bin. So 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1. 1 times 2 is 2, remainder 0. 1 divided by 2 is 0, so we know we're done, right? 0 times 2 is 0 with remainder of 1. Our final answer is 1, 0, 1.
So you don't care if it's 4 bits?
Well, no, for those you don't, I don't care for how many bits. Yeah, that would make it a lot harder if you were forced into a number of bits. So what we need to do for a problem like this, so if we're writing this function, we want to keep going. We want to keep doing something as long as the value we're currently looking at is not a 0. Right? We want to keep doing something as long as the value is not currently a 0. Is the value currently a 0? No. What's the something that I do? Divide by 2, and I record the remainder. Make sense? Now I have that value. Now one thing, I actually need to look at this real quick. I think this might not give me, yeah, so I need. Let me quickly give you scheme integer division. Otherwise, your life will be a lot worse. So we have a function called quotient that allows you to do integer division. 5 divided by 2 using quotient will give you the 2 instead of the 2.5. All right, so what do we want to keep doing? As long as the value we're currently working with is not a 0, we want to calculate the remainder and calculate my other number. And do what with those two values? Call the function again. So we're actually going to have this function. Now, you could do it one of two ways. We can either say we're going to start this off with n and a list. So what we're going to do is we're going to pass along the value that we're currently working on and the list that we're currently building. So initially we have a nothingness. We have an empty list that has nothing in it. We'll ask the question, if equal n 0, what do we want to do? We want to return our answer. But our answer has actually been built in reverse. So for right now, I'll just say boil on the list. We'll see it's backwards here in a second. Else, so if it's equal to 0, we're done. Else, what do we do? I'm going to call des2bin, passing it quotient n2. That's going to be my new starting point. And passing it a list that is the cons of modulo n2 along with whatever list currently is.
Does cons push it on the beginning or the end?
It pushes it onto the front of it. So we're building it backwards.
Okay.
So if I say des2bin, and the way I would call this is since I'm passing it a number as well as my starting empty list, we can create a helper that forces the empty list thing. I'm going to say a 5, and then I'll go ahead and give it my initial empty list. It's going to give me that 1, 0, 1. But now we're not necessarily sure what order it put it in. So let's change that. Let's say des2bin. Let's do a 7. That's still a bad one. See, these are computer science jokes. Right?
Or you just did 2.
2. Yeah. des2bin 4. So we were building it in reverse. Make sense? Now, if you wanted to make it a little cleaner, what we would do here is we would say define des2bin just takes in, I'm going to call this guy des2bin helper. We're going to call this guy des2bin. And this guy is going to be a lambda that takes in an n and returns des2bin helper, passing it n and starting it with the empty list. And then we just need to make sure we recursively call our des2bin helper here. So des2bin helper, that's the guy that actually does all the logic. We just have a function here called des2bin that allows us to just pass in a 5 or a 4 or a 7, and it goes ahead and gets the ball rolling with the empty list for us.
Do we not have to worry about doing the decimal to binary then, since we technically
I just did it.
Yeah, so.
You do have to do it, but you could just use what I did.
Okay.
I would strongly encourage you to study this and make sure you understand how it works. So des2bin, bypass in 4, gives me my answer. So des2bin takes in a single value, and what does it do? It calls des2bin helper, passing of that value along with that empty list to get the ball rolling. Make sense? All right, so I'll put all this code up on Slack so you have like a how do we do a code snippet?
Oh, you do the attachment. I figured.
Create new code snippet. Call this homework 1 starting point. Create snippet. And then what I'll do is I'll just grab all this and I'll put the assignment up. Oh, awesome. Yeah, I see them all the time now because with that, because this thing, it doesn't matter if you save your password, it doesn't even matter. It doesn't even matter if I hit never. It's doing something with like auto removing cookies or something like that, which is fine. But just believe me when I say never. Don't ask me again. They're doing something pretty funky with the site these days.
Do you see Corey in Acuity at all?
I have, yeah. He plays Pong.
Let's see.
It's the thing to do.
Pong.
2 o'clock Pong time.
So that's like cool kids called ping pong.
I don't know if it's
The cool kid.
Oh man, that doesn't come out into the format I want it to come out in.
That's not me, but I hope that was okay.
Thanks, Ryan.
You're welcome.
All right, so
When are we going camping? When are we going camping? You want to do camping too? Yeah, I think we should go back to Polar in September or October. So we could do something. And do another haylock and chill. Oh my goodness, question.